this question here is another common question. On the left, we've got a net of a box, okay, and it's a piece of cardboard or something that is 6 by 6 centimeters, let's say, and you can cut out a square from each corner with a length of x. Okay, so you cut out a square from each corner, so that means that this bit goes, and this bit. You cut those bits out. You decide how much to cut out, and then you fold up the sides, and it makes a box. Okay, and this is the box over here. So let's see if we can say what the sides are. How high is the box going to be? X. Now, guys, what's the length for this box here? It's not 6, because you 6 take away 2x, yeah. Because it was 6 long, and I've taken that bit off and that bit off. Okay, got it? And so what's this length here? Say again? Same, yeah, 6 minus 2x. You got it? Okay, so what's the, let's write down an expression for the volume of the box. Remember, we want to maximise the volume of the box. So how do you find the volume of a box? It's length times width times height. So it's just going to be x times 6 minus 2x times 6 minus 2x. Yeah? So I've just got to multiply all of this out. Okay? Because as it stands, remember, if you want to find the maximum or a minimum, you differentiate and you put it equal to 0. Okay? But I can't differentiate that at the moment. I'm going to multiply this out. Is this going to be a C1 sort of question or a C2 sort of question? It's going to be C1. Why is that? Yeah, when I multiply this out, I'm just going to get squares and cubes, which are just okay. There's not going to be no fractional indexes or okay. Right, so let's see if we can multiply it out. Shall we multiply these two brackets out first, the 6 minus 2x and the 6 minus 2x? So let's multiply those out first. So I've still got v equals x. What am I going to get when I multiply these two brackets out? 6 times 6. Very good. And then let's do 6 times minus 2x.
12.
Minus 12. And then I've got minus 2x times 6. Is that another minus 12x? And then I've got minus 2x times minus 2x. Plus 4x squared. Good. Yeah. Helen? Is that okay? I could just tidy this up because there's a minus 12x and another minus 12x, isn't there? So let's write this as like this, shall we? 4x squared minus 24x plus 36. You happy with that? And now I just need to multiply it all through by x. So I'm going to get 4x cubed minus 24x squared plus 36x. You happy with that? Okay. So now, again, I've got v, the volume, as a function of x. Okay. It only depends on x. So I could plot a graph of this, and it would be a cubic, so it would have a maximum and a minimum. Okay. So we're going to try and find out where the maximum and minimum are by. So we're going to differentiate it, and we're going to put that gradient equal to 0, because the gradient's 0 when it's a maximum and minimum. So who wants to differentiate it? Did you just say me then, Emily? No? Does it? Ow. Glasses are meant to be good for your eyes, aren't they? But Amelia, how do you differentiate that? Yeah. Plus 36. Cool. Is that good? Okay. And now we want to write down this statement. It's stationary. Stationary when dy dx equals 0. Okay. So now we just put 12x squared minus 48x plus 36 equal to 0. Do you agree? Okay. So we just want to know when this 12x squared, and it's just a quadratic, isn't it, to solve? 56. We want to put it equal to 0. Now, the numbers are nice because we can do what to it? By dividing by 12, yeah, can divide by 12, so we'll get x squared. What's that going to be? Minus 4 plus 3 equals 0. Can we factorise it? What was it, sorry? No, I don't think so. Is it minus 1 and minus 3?
Yes.
Yeah? Minus 3 and x minus 1. Minus 3 times minus 1 makes 3, and if I add them together I get minus 4. That's right, isn't it? So what are the actual answers then? What are the values of x that make this maximum or minimum?
1 and 3.
3 and 1. Now, which one of those values is going to make this, we want the volume to be maximum, don't we? So we've got two values. We've got two values of x that are going to make this stationary. So that's either maximum or minimum, okay? 3 or 1. So x can be 3 or 1. 1's going to make it maximum. Yeah? You're absolutely right, yeah. So, well, what happens if if x is 3, what happens? Yeah, if x is 3, that means I'm going to be cutting 3, I'm going to be cutting 3 out from this side, and 3 out from that side, and what do we get? Nothing, okay? So that's obviously a minimum, right? Okay, so minimum volume. So yeah, the value of x that makes this thing maximum is, not that one, sorry, when x equals 1. But remember, we've just found how much you need to cut out of the corner, okay? But the question was saying, what is the maximum volume? So how would I now find the maximum volume? Sub this value of x in. So should we just quickly do that? We had an expression for the volume, and what was it? It was x times 6 minus 2x times 6 minus 2x. Was that right? And we're going to sub in when x is 1, because that's the value that gives us the maximum. So when x is 1, we get 1 times 6 take away 2 times 6 take away 2, which is just 4 times 4. Is that just 16? So the maximum volume is 16 centimetres cubed. And it doesn't matter what other value of x you cut out, you won't get a volume that big. We're trying to find the maximum volume of the cone, and we've got all we actually know about the cone. We know just one thing, just the side length, the slope length. Okay, so we can find the maximum volume of a cone just by knowing the slope length. Now, I can change h and r. So if I wanted to, I could make h longer. Can you see this, Charlie? I can make h longer, but I've got to keep that's always 18. So if I make h longer, what happens to r? It gets shorter. Or I can make r longer, and then it wouldn't be as tall, cone, right? But 18 is always 18. So all I know is the slope length. Now, we want to maximise it, so we're going to differentiate v and put it equal to 0. What's the problem with my equation for v at the moment? It's got two variables, so I need to get rid of one of the variables. I'll probably get rid of the h. Now, Matty, I think you spotted how to get rid of the h, right? Yeah, do you all agree with this statement? Look, 18 squared is equal to h squared plus r squared. Is that true? Why is that true? It's Pythagoras, yeah? We've got a right angled triangle here. So that means that h squared must be equal to... In fact, hold on a second. So... In fact, that means that h squared equals 18 squared take away r squared, doesn't it? Okay. Now, I'm looking at it now and I'm thinking, is it better to get rid of the h or better to get rid of the r? It's probably better to get rid of the r, because I could write down equally validly r squared equals 18 squared take away h squared. Do you agree with that statement as well? So they're just different ways of writing Pythagoras. Now, if I use the r squared and swap that instead, there's an r squared in the formula, so it's just a direct swap. Can you see that? Okay, so I'm going to write out my equation for volume again, but where there's an r squared, I'm going to write 18 squared take away h squared. So I get 1/3 pi times 18 squared minus h squared times h. Okay? And then I'll just multiply this out. So I've got v equals 1/3 pi. What's 18 squared, do we know? This is 324h. Okay. Minus h cubed. Because I times everything by h there. So I'm going to get here, I'm going to divide everything through by 3. So I get 324 divided by 3. Now what's that going to be? Is that 108? I think that's 108 pi h. And then I'm going to get minus h cubed pi over 3. Is that true? I think that's alright, isn't it? Okay, can I differentiate that now? It's just got h's, isn't it? So I'm going to do dv dh. And let's see if one of you can differentiate it. 108 pi h, what does that differentiate to? So 108 pi h, what does it differentiate to? Yeah, so it's 108 pi. Okay, so this one here I've got minus, this one's here, minus pi over 3, that's the coefficient, h cubed. So when I differentiate this, what would I get? I times by 3. So when I times that by 3, I'm just going to get, I just get rid of the 3 on the bottom, so I get pi h squared, is that right? Okay. I want this to be 0, so it's stationary. It's stationary when dv dh equals 0. So I'm going to take this and put it equal to 0. So I'm going to get 108 pi minus pi h squared equals 0. So that means that pi h squared equals 108 pi. I can divide both sides by pi because it's just a number. So I've got h squared equals 108. So the h value is going to be the square root of that. Okay, which will be like 10 and a bit, isn't it? So what's the square root of 108, do we know? 10 point what? Is it? 10.4, should we say? Brill. Okay. So that's going to be the maximum volume when h is that. We're going to do this optimization problem, and this question is going to be more for the Core 2. So you get optimization questions in C1 and Core 2, but the only difference is really what you're being asked to differentiate. And do you know what the difference is between the Core 2 differentiation and the C1? It's that you have to do that bit at the start where if it's got a fractional power, you have to, if it's like a root, you have to write it as x to the half, or it could have a negative power. So the difference between C1 and C2 is just that. The thing you have to differentiate is slightly harder, but you solve the problems exactly the same way. So we'll do a Core 2 style question. And what we've got is we want a cylinder to hold a certain amount of volume. And the volume we want it to hold is 330 cubic centimetres. That's the same as like 33 centilitres, so like how much a can of Coke holds. Okay, that's going to be the volume. So I'm going to put some things on here. So that's going to be the radius, and then we've also got this value of the height. Okay, and what I want you to do first of all, because this is usually how the problems work, we want to make a cylinder that holds 330 centimetres cubed volume, but we want to use the least material as possible. Okay, that's the idea. So we want the surface area to be as small as possible. So what I want you to do first of all, I'll give you a couple of minutes, is write down an equation for the volume of that thing and write down an equation for the surface area of that thing. That's going to be the starting point of these problems, always the same. So write down what is the volume in terms of R and H and what is the surface area in terms of R and H. Okay? So let's have a look then. What did you get then for the volume? Equation of the volume. How can you write down the volume of this thing in terms of R and H? How do you find the volume of that shape? It's like a prism. Say again. No, you find the area. It's a prism, so you find the area of the cross section. Find that area and then times it by the height. So what's that area then? It's the area of a circle. It's going to be a circle. No? Pi r squared, right? Okay, area of a circle is pi r squared. Okay, and then I times it by h. Okay, so that's the volume of that shape there, do you agree? Yeah? That's how we find the volume. Any prism that you've got, could be a cuboid or cylinder, or a triangular prism, you find the area of the cross section and you times by how high it is, okay? And so what about the surface area then? I'm going to use S for surface area. Surface area is the flat areas of all the bits that make it. So what sort of shapes make this cylinder? Well, there's a circle on the top. So there's a circle on the top. There's a circle on the bottom. And what's the shape that goes around the middle? It's going to be a rectangle. Okay? It's like the baked bean sort of label. Okay. So what's the area of the top bit? Pi r squared. What's the area of the bottom bit? Pi r squared. Now we've got to think about this. What's the area of this rectangle here? Well, what's this length here? H, because that's just how high it is. And then this length here goes all the way around a circle. So it's the circumference of a circle. And so what's the formula for circumference of a circle? Pi times the diameter. But we're using R, not D. 2 pi r, yeah. Okay. So that length there is 2 pi r. Okay, you got it? So my surface area total is going to be the area of the top and the area of the bottom. So that's 2 pi r squared plus 2 pi r. Do you agree with that? And that's all the areas. The area of the top bit is pi r squared, area of the bottom bit is pi r squared, and then I've got 2 pi r at the bottom. Yeah, and times by h. Well done, Em. I need a h on the end, right? Because it's a. Okay. Right. Is everyone happy with that? Okay. So I've got an expression for the volume and I've got an expression for the surface area. But I also know that the surface area, this 2 pi r squared, I also know that the volume is going to be 330 centimetres cubed. Okay, is that right? And that's usually how these questions are phrased, right? You have, if it's a shape, you've got the volume, you've got the surface area, and you'll know one of the two things. It will usually give you a value. And what do we want to minimise? Yeah, why would you want to minimise the surface area? We want it to hold this much like Coca-Cola, but we want to minimise the amount of packing material, like the aluminium made in the can. So we want to minimise the surface area, S. Okay. Now I could plot a graph of S against R, and it would change like this. How do you minimise something? How do you find the minimum amount of something? Yeah, you differentiate it, and you put the differentiation is the gradient, and you want the gradient to be what? 0, yeah. Okay, we'll talk about that in a second. The trouble is, if I want to differentiate this, which is what we're saying we're going to do, we're going to differentiate this. At the moment, there's two variables in it. There's r's and there's h's. And I can only differentiate it with respect to r or respect to h. So what might be a good idea is to get rid of that h. Can anyone see how I could get rid of the h? It comes from the extra bit of information you got. Can we write down an expression for h equals all on its own? Brilliant, Shannon, okay. From here, look, we've got pi r squared h equals 330. So that must mean that h equals 330 divided by pi r squared. Do you agree with that? Okay. So we want to minimise s, and to do that, we're going to need to write this equation with just r's in. Okay. So all I do now is I write this out, 2 pi r squared plus 2 pi r, and where I had a h before, I don't want a h, I just want things with r's in, so I'm just going to write down what Shannon said h was the same as. Can you see that? And now my expression for the surface area only has r's in, only has one variable. Okay? Now, if I were to plot a graph of s in the y-axis and r in the x-axis, then it would be a graph that changed like that. I could plot this curve here, and it'd be a graph that changed, and there would be some values where there was a maximum surface area, and there'd be a place where there was a minimum surface area. Okay? But at those places, the gradient of the line would be 0. Can you see that? Okay? So what we're going to do is we're going to differentiate this and find out what it is and put it equal to 0, and that's going to be where it's maximum or minimum. Okay? Where it's a stationary point, we say. Okay? Now, before we differentiate it, this is what we were doing the other day. This is why this question here is a C2 question and not a C1 question. Because some of the r's are fine to differentiate. This thing here is okay to differentiate. But this thing here, the r squared's on the bottom. So we're going to try and rewrite this out so that we can get it into a form where we can differentiate it. Okay? So that's the next step. Get it into a form where we can differentiate. Okay? So, let's have a look. We've got s equals 2 pi r squared. That's fine. And now I've got to multiply this out. So I'm going to multiply 2 pi r times 330 over pi r squared. Well, 2 times 330 is going to be 660. And I've got pi r. So I've multiplied the top by 2 pi r. Can you see that? And then I divide by pi r squared. So that's what was on the bottom. Yeah. We're just trying to make this now into a form we can differentiate it. And you should see that, look, because it's a fraction, I've got a pi which cancels with a pi on the bottom. Yeah? And I've got an r which cancels with one of the r's on the bottom. And so I can write this out again as the surface area equals 2 pi r squared plus 660 over r. Do you agree with that? Right, Becky. This 660 over r, right? How can I rewrite that so that I can differentiate it? I don't want the r to be on the bottom. I want it to be up there. So at the moment the r is on the bottom, yeah? Yeah? So that's not changed, but what's changed here? Can you rewrite that? At the moment the r is on the bottom. So what would that mean in the power? Yeah, brilliant. So it's going to be 660 times r to the power of minus 1. Okay? And now I'm ready to differentiate it. Okay? So let's just quickly talk about what we've done, and then, because the next bit of the problem is just differentiating. This is usually the bit of the problem that people struggle with. We wrote down an expression for the volume, we wrote down an expression for the surface area, and we want to minimise the surface area, so we want to differentiate it, but we can't differentiate it because there's a h in it. So Shannon showed us how we could swap the h for some lots of r, and we put that in over here. and then we've just had to rearrange it by just using laws of indices to a form now where we're ready to differentiate. Okay, so the next step is we're going to differentiate and we're going to put it equal to 0 because the graph is going to be stationary when the differentiation is 0. So let's see if one of you guys can differentiate it. I want to do ds, differentiate s with respect to r. So what do I get? Remember, pi is just a constant number. So what do I get when I differentiate that? 2 pi r squared, what does that go to? 4 pi r. And then 660 r to the minus 1, what would that go to? Minus 660 r to the negative 2. Brilliant. And when I'm going to solve this, in a minute I want this to, in fact, let's just do this as a separate step. You're absolutely right with the differentiation, you got 2 marks if it was a question, okay? And now we want to, and you want to write this statement, you want to say, it's stationary, or the graph is stationary. What do I mean by stationary? Yeah. Or it's a maximum or a minimum. The graph is stationary when the s, the r equals 0, and that's what we're trying to find out, the stationary point. So I take this thing, 4 pi r minus 660 r to the minus 2, and I want it to be equal 0, and we're trying to find the value of r that makes it 0. Okay? So how can I solve this? Now, what I said the other day was, when you differentiate it, you want it in this form with the indexes with the negatives in. But when you're actually trying to solve it, it's probably better to write it in the other form where the r is on the bottom, you see. So can someone write this back how it sort of originated with the r on the bottom? Do I have to do anything with the first bit? No? But what about this second term I've got? Minus 660 r to the minus 2. What would that be the same as? Brilliant. Okay, and I think you'll find that easier to solve now. So should we try and solve it? What would be the first thing I do? Move this second bit over, yeah. So what I should get is 660 r squared equals 4 pi r. Do you agree with that? Yeah. Next thing? Times it all by r squared, so I get 660 equals 4 pi r cubed. Do you agree with that? Next thing? Remember, I just want to know what r equals, really. So what would be the next? Say again? Yeah, I can move the 4 and the pi, because they're both just numbers. So now I'm at this point. R cubed equals 660 over 4 pi. Okay? And then cube root. Guys, can you quiet down a little bit, please? So you should be able to just do that on your calculator. Okay, I think I've got a calculator here somewhere. Is that it? So what was it? 660 divided by 4 pi?
Yeah.
Yeah? Pi's down there, isn't it? Okay, and then cube root that. So how do I do a cube root? It's this one, isn't it? I don't know how to do it. Cube root. Oh, wicked. Of the answer, yeah. 3.7449. Okay. So what we're saying, 3.7. Okay. So what we've actually found out now is there's a value of r that makes the gradient 0. Okay, and it's 3.7 centimeters. So that means that this value of r either makes it a maximum value or a minimum value. Okay, so then remember how we can check with it, which one's which. You differentiate again. Okay, and if it's a positive value, then it's a then it's a minimum, and if it's so I've just got to differentiate this again. Now I'm going to save you the problem. This one's going to be a maximum. Okay, Well, you can differentiate again and check if you want. You differentiate again and you put the value 3.7 in it, and all you're looking for is it positive or negative. Okay. But this one's going to give you this one's going to give you a minimum surface area. Okay. This is what gives you the minimum surface area. So it says if we have a can like this and we want it to hold a certain volume, 330, then the minimum surface area, the minimum amount of aluminium we would need is when R, that R there, is 3.7 centimetres. And that is pretty much what a Coke can is. Okay, so this is like a can of, I wonder if I can do it, Coca-Cola. Okay. Like that. Okay, so 3.7 centimetres is pretty much the radius of a Coke can.